So, sequences and series. Before we talk about the specific types of sequences that you're supposed to know about on the IB exam, I think it's worth noting in general what a sequence is, because sometimes these might show up more generically on paper 3. And a sequence is nothing more than an ordered list of numbers that are arranged according to some pattern. And that pattern can really be anything you want. And the types of sequences we're going to be interested in are going to be specific types of patterns. So for example, I might have the pattern 2, 4, 6, 8, 10, which is a pattern where I add 2 every time. I might have 1, 1/2, 1/4, 1/8. That's dividing by 2 every time. Or I could have 3, minus 1, 4, minus 1, 5. And the pattern here is I'm going a positive number, then I'm going to -1, then I'm going to one number bigger than the positive number. So 3, 4, 5, alternating with -1. That's not a pattern that you would really see on the IB, but just so you know, these patterns can really be anything. And we usually denote these with UN. So we say the first term is U1, second term U2, etc. And we say UN is the nth term in the sequence. Okay. And there are specific types of sequences, namely arithmetic and geometric, that we need to know about on exams. So let's talk about arithmetic sequences first. These are probably the most basic type of sequence. And it's essentially a sequence where the rule for going from one term to another is simply adding a constant term. So in this case, I go from 1 to 6 by adding 4. I go from, by adding 5. Erase that. I'm going 1 to 6 by adding 5. I'm going to 11 by adding 5, and so on and so forth. At each step, I'm going to add 5. The next sequence is not arithmetic because to go from 2 to 5, I have to add 3. But to go from 5 to 9, I have to add 4. So that would not be arithmetic. And that is probably pretty basic. Let's maybe do a bit of a harder example. If I have 2k plus 3 and 11 as consecutive terms in an arithmetic sequence, and I want to find k based on that fact. So if terms in an arithmetic sequence, that means that the difference between any two consecutive terms is the same. And we call that difference the common difference d. And that's what defines an arithmetic sequence. You have a common difference, which means that if my terms are 2k plus 3, and 11, that means I added d both times to go from one to another. And if I added d, that means I can isolate d by doing 11 minus 2k plus 3. And that should be the same thing as 2k plus 3 minus 2. Okay? And if I rearrange all of this, I'm going to get 13 is equal to 4k plus 6. And that's going to give you 7 equals 4k, k equals 7 over 4. Let's move on. I'm going to give you guys a minute to try this exercise, and then we'll continue. Let's look at this first sequence. I have 3, 7, 11, 15, 19. To go from 3 to 7, I add 4. Same thing for going from 7 to 11, 11 to 15, 15 to 19. So that is an arithmetic sequence, and the common difference is 4. Now in part B, I go from 2 to 6 by adding 4, but I go from 6 to 12 by adding 6, which means the difference between 12 and 6 is not the same as between 6 and 2, so this cannot be an arithmetic sequence. Finally, I go from -5 to -2 by adding 3. This is a little bit trickier when you have negative numbers, but I added 3. And then I'm going to add 3 again to get to 1. Plus 3 gets me 4, plus 3 gets me 7. So arithmetic with d equals 3. Nice. All right, I'm going to give another 30 seconds to work on this exercise, and then we'll continue. All right, let's go over this. So I have the consecutive terms, 2 plus k, k minus 1, and 8 minus k. And if this is an arithmetic sequence, then the common difference, the difference between each pair of terms, consecutive pair of terms, has to be the same. That means that 8 minus k minus 1, third term minus second term, has to be the same as k minus 1 minus 2 plus k. And if I simplify this, on the right-hand side, I'm going to have 9 minus, left-hand side, sorry, 9 minus 2k is equal to, it's going to be -1, -2 is -3, and I'm going to have k minus k. Those are just going to cancel, which means that I'm going to get 12 is equal to 2k, which makes k equals to 6. All right, so now that we understand the pattern in an arithmetic sequence, how we go from one term to the next, we can actually think about finding the general term, any term that we like in an arithmetic sequence. So if I start with a first term u1, and each time I go to the next term, I'm going to add d, then I know that if I go to, let's say, the 7th term, that means that I went from 1 to 2 in terms of the terms to 3 to 4 to 5 to 6 to 7. How many jumps have I made? I've made 1, 2, 3, 4, 5, 6 jumps. And it's 6 because I started at the first term and I didn't start at 0. So I went from u1, I added d again, and again, etc. And I added it 6 times, which means that u7 is equal to u1 plus 6d. And in general, I can write un is equal to the first term plus n minus 1 times d. So the important thing to notice here is I'm starting with my first term and I'm adding d some number of times, and that number of times is the n of the term minus 1. And I'm doing minus 1 because I start at u1 and I don't need to add d to get u1. So if you plug in, n equals 2 into this formula, you would find u2 is equal to u1 plus d, which is what we'd expect. So quick example here. An arithmetic sequence has u3 equals 5 and u7 equals -7. And we want to find the first term and the common difference. So we know that u3 can be written as u1 plus 2d, and u7 can be written as u1 plus 6d. That was just using the formula that we just talked about. And now if I subtract one from the other, so this is just trying to eliminate one variable, I'm trying to eliminate the u1, I'm going to get u7 minus u3 is equal to u1 plus 6d minus u1 plus 2d. That's on the left-hand side. And on the right-hand side, I get -7 minus 5. And that simplifies to 4d is equal to -12. That's going to tell me that my common difference is -3. And I know that the third term was 3, which means that I can subtract, the third term is supposed to be 5, which means if I got to the third term by adding d twice, in this case -3 minus 3, and this is equal to 5. So I can undo that by adding back 3 and adding back 3, and I find the first term was 11. So again, I'm going to give you guys 30 seconds for this exercise. Okay, so I'm looking for the 11th term, and I'm given that un is 4 minus 3n. So all I have to do is plug in n is equal to 11. So I'm going to have 4 minus 3 times 11 is 4 minus 33, and that's -29. This one I'm going to give you a minute to solve on your own. All right, let's go over this. So I have the 8th term in my sequence is u. The 8th term in my sequence is u8, and that's equal to 31. And the 15th term, u15, is equal to 59. And I can write u8 as u1 plus 7d, that's equal to 31. And then u15 is u1 plus 14d, it's equal to 59. Now if I subtract one from the other, if I do u1 plus 14d minus u1 plus 7d, the u1s are going to cancel, and I'm just going to get, and this is supposed to be equal to 59 minus 31. And on the left-hand side, I'm left with 7d is equal to 28, which means d is equal to 4 is the answer to part A. And now, calculate the 100th term in this sequence. All right, so I have u8 was u1 plus 7d, and I know d is 4. So that's times 4, and I know that u8 is 31. So that means that I have u1 plus 28 is equal to 31, which makes u1 equal to 3. And then To find U100, the 100th term, I do U1 plus 99D, and that's equal to 3 plus 4 times 99. And 4 times 99, I'm going to do 4 times 100, and then minus 4. So it's going to be 3 plus 400 minus 4. That's going to be 400 minus 1 is 399. Okay, 399. Next, let's talk about geometric sequences. These are a little bit trickier. In the same way that an arithmetic sequence was defined by having a common difference, right? If I subtract one term from the term before it, I always find the same difference, D. A geometric sequence is one where the ratio between consecutive terms is constant, and we call that constant the common ratio R. So, for example, if I have the sequence 8, 2, 1/2, 1/8, that's a sequence where I'm dividing by 4 every time, which makes that sequence geometric. But the sequence 3, 6, 9, 12 is not geometric, because if I do 9 divided by 6, that's 3 over 2. But if I do 6 divided by 3, that's equal to 2. So the ratio between the second and the first term is not the same as between the third and the second term, so it can't be geometric. Let's take a look at an example here. We have a sequence 2, comma, k minus 1, comma, 8. When is it geometric? Well, if it's geometric, like I said, there has to be a constant ratio between consecutive terms. So the consecutive terms here are 2 and k minus 1, and then k minus 1 goes to 8. So that means that 8 divided by k minus 1, that should be r, but r should also be k minus 1 over 2. So I can actually equate those two. And if I cross multiply my fraction, I'm going to get k minus 1 squared is equal to 2 times 8, 16. And that will give you a quadratic, and you can factor that quadratic to find the two possible values of k. So I'm going to give you guys 30 seconds to try this exercise. Okay, so we're looking for the one of these sequences that is geometric. So only one of these is supposed to be geometric. Let's look at the first one. I do 4 1/2. To go from 4 to 1/2, I divide it by 8, right? Because I divide by 4, I get 1. I divide by 2 again, that's dividing by 8. But to go from 1 over 2 to 1 over 8, that's dividing by 4, which is different than dividing by 8. So that's not geometric. Then from 1 to minus 3, I multiply by minus 3. I multiply by minus 3 again, and I get 9. But if I multiply by minus 3 again, I would get negative 27 and not positive 27. So that's not geometric. Then I have 2, 4, 6, 8. That's adding 2 each time, but it's not multiplying by 2, because 2 times 2, 4. But then 4 times 2 is not 6. So that's not geometric, which means, sort of by elimination, the last one has to be geometric. I go from 1 over 32 to minus 1 over 4. And this is maybe a little bit harder to see what the ratio is, so I'm going to write it out. R is equal to minus 1 over 4 over 1 over 32. That is equal to 32 over minus 4, which is equal to minus 8. That is option 1. Okay, next question. I'm going to give you probably I'll give you, 2 minutes to solve this one because it's a little bit harder. But let's go over the solution. So again, if these terms are consecutive in a geometric sequence, then I need to, I can equate the ratios between consecutive terms. So 12 over k plus 1 is equal to k plus 1 over 3, which means that 36 is equal to k plus 1 squared. And I can actually take the square root of both sides. That's a little bit easier. So k plus 1 is equal to plus or minus 6. So I either have k is equal to 6 minus 1 or minus 6 minus 1. That's going to be 5 or minus 7, option 4. So in the same way that we had a general term for the arithmetic sequence, right? We had a formula for finding any given term in an arithmetic sequence. We have a similar formula for finding any term in a geometric sequence. So if we started with the first term and we multiply by r to get to the second term, multiply by r again to get to the third term, etc., then each time to get to the nth term, we've multiplied the first term by r and then r again. And we multiply n minus 1 times by r. And again, it's the same n minus 1 as we had in the arithmetic sequence because we start with the first term. That's where we're starting. So we have to subtract that 1. We didn't multiply by r to get to u1. And to get to u2, we multiply r once. So that's 2 minus 1 is 1. So multiplying by r and n minus 1 times is just r to the power of n minus 1. And this is the formula that you have for your geometric sequence. And this is in your formula booklet. So let's do an example. If I have a geometric sequence that has second term 9 and fifth term 1 over 3, find the first term and the common ratio. Okay, so let's use the formula. I have the second term is the first term times r is equal to 9. And the fifth term is u1 times r to the power 4. That's equal to 1 over 3. Now, if I divide u5 by u2, I get u1 r4 divided by u1 r. That simplifies to r cubed. And then 1/3 over 1/9 is 1 over 27. And then to take the cube root of 1 over 27, I just recognize that 27 is 3 to the power of 3. So this becomes 1 over 3. All right. So if r is 1 over 3, that answers one part of the question. And to find the first term, we just have to work backwards from the second term. If the second term was 9, that means we multiplied by r from u1 to get to 9. So u1 times r, which is 1 over 3, gave me 9. So how do I go backwards? I divide by r. So I do 9 divided by 1/3, which is the same as 9 times 3 is 27. And I'll give you a minute to try a similar example. This is a calculator question, by the way, so you can use either your TI-84 or whatever you use. You can also just use your iPhone calculator because this is not too complicated. Okay, so I have a third term, v3, and I'm using v here, which is sometimes common for geometric sequences to use v instead of u, but it makes no difference. It can be v, a, whatever letter you want, really. That's equal to 2, but it's also equal to v1 times r. That's equal to 2, and v6 is equal to v1 times r to the 6 minus 1 is r to the 5, and that's minus 54. So if I do v6 divided by v3, I'm going to get v1 r to the 5 over v1 r is equal to r to the 4, and it's supposed to be also equal to minus 54 over 2, and that would give me minus 27. And I made a mistake here. v3 is v1 r squared. That's r squared, and it makes this r cubed. That wouldn't have worked otherwise. So that means that if I take the cube root of both sides, I get r is equal to minus 3, which means that the first term is v1 is equal to v3 over r squared. So that's 2 over 9. And that means that the 11th term, v11, is equal to 2 over 9 times minus 3 to the power 11 minus 1. That's negative 3 to the power 10. I'm going to use my calculator for that because I do not know how to do that in my head. So I get minus 3 all to the power of 10. It gives me 59,049. If I multiply that by 2 and divide by 9, I find 13122. And that's the final answer. Next slide. All right, so we're going to do a slightly harder exam style problem now. And like I said earlier, I'm not going to give you guys time to start on your own because we have so many problems to go over today that we just will run over time. I recommend, if you want to try this on your own, mute me, don't listen to me, try it on your own. I'm going to solve it at, the pace that you would need to do it on the IB, so 8 minutes. And if you don't have it by the time we're done, you can come back, and these are all recorded anyway, so you're not going to miss anything. So the first, fourth, and 10th term of an arithmetic sequence are consecutive terms of a geometric sequence. This is a classic IB question. It's been showing up. It showed up on the previous syllabus, and it's all still showing up on the current version. You can see that it's marked here on the website by 2 exclamation marks, which means it's very common on IB exams. All right. But let's write out what we know. I have the first term in an arithmetic sequence is u1. The fourth term is u1 plus 3d. And the 10th term is u1 plus 9d. And those apparently are consecutive terms in a geometric sequence. And that means that they form a common ratio. If I do the 10th term of the arithmetic sequence divided by the 4th term, I should get r, and the same for 4th term divided by 1st term. So let's write that out. u1 plus 9d over u1 plus 3d is equal to u1 plus 3d over u1. All right, I'm just going to move my face so that we can see a little bit better. There we go. A bit more room now. And I'm going to cross multiply here on both sides. So I'm going to get u1 times u1 plus 9d is equal to u1 plus 3d squared. And now I need to expand this. So I'm going to do, on the left-hand side, u1 squared plus 9d u1. And on the right-hand side, I'm going to get u1 squared plus 6d u1 plus 9d squared. All right. Now it's nice. I can cancel u1 squared on both sides. And then I'm left with a 9d u1 on the left and a 6d u1 on the right. So I'm going to cancel this 6 and put a 3 there. So 3d u1 is equal to 9d squared. And now, when I have an arithmetic sequence, I can't have d is equal to 0 because that wouldn't actually be an arithmetic sequence. I wouldn't actually be changing. I would be starting with the first term and the same term and the same term, which means that I can cancel. I can say d is not equal to 0, so I can divide by d on both sides, which means that 3u1 is equal to 9d, which tells me that u1 is equal to 3d. Now, this is a bit of a tricky problem, but we're almost done with part A. I remember that I had an expression for r, which was r is equal to u1 plus 3d, u1 plus 3d over u1. And we just realized that u1 is the same thing as 3d. So I can replace this 3d with u1. And then this becomes 2u1 over u1 is equal to 2. And so my answer for part A is r is equal to 2. And now part B. So we're given that the sum of the first 4 terms of the geometric sequence is 45. All right. So it clearly mentions here the geometric sequence, which we have to pay special attention to. It means we're not looking for the sum of the arithmetic terms. But if I write out what I have in my geometric sequence, I found that I have r is equal to 2, we said. And we know that u1 was equal to 3d. That's what we found in the previous question, okay? And now I know that the sum of the first 4 terms in the geometric sequence is 45. What does that mean? Let's write it out. The first term is u1 in the geometric sequence. The second term is u1 times r. The third term is u1 r squared, and the fourth term is u1 r cubed. And that's all equal to 45. But I know what r is, so I can actually plug in my specific r, and this becomes u1 plus 2u1. I square 2, I get 4u1. 2 cubed is 8u1, all equal to 45. So if I collect my u1 terms, I have 1, 2, 4, 8. That's 3 plus 4 is 7, plus 5 plus 8 is 15. So u1 times 15 is equal to 45, which means that u1 is 3. And that is my answer. So let's talk about series now. I think I skipped a slide. What is a series? So a series is the sum of terms in a sequence. So if I have a sequence 1, 2, 3, 4, then the corresponding series would be 1 plus 2 plus 3 plus 4. We're basically adding up the terms that we had in the sequence, in our pattern. And because the sequence, the series can continue forever, we usually write S with a little n underneath to denote the first n terms in the series. So if I have the series 1, 2, 3, 4, then I can say Sn is 1 plus 2 plus ... and I'm going to stop at n. So n is the last term that I add. All right. Let's do a specific case of the arithmetic series. So if I have an arithmetic series, I know that I have a common difference between between any two consecutive terms. And these two formulas are in your formula booklet in terms of how you calculate the sum of n terms using the first term, n and d. All right, so that's always available to you, but I want to try and understand where those formulas came from and how they work. So let's imagine you have the series 1 plus 2 plus 3 plus ... up to 1,000, right? The way you can think about this formula is to imagine writing the sum vertically. So I'm going to write 1, 2, 3, 4, ... all the way down to 500. And then I'm going to wrap and work my way back up. So I'm going to write 501, 502, 503, etc., up to 1,000. So why am I doing that? Basically, I'm wrapping the sum onto itself so that I can match up each term with a corresponding term on the other side of the sum. So I match the first term 1 with the last term 1,000. I match the second term 2 with the second to last term 999, third term with third last, etc. And when you do this, you'll realize that because of the symmetry, because we're adding the same thing every time, if I add the first and last term, second and second last, we're always going to get the same thing, right? 1 plus 1,000 gives me 1,001. Same thing for 2 plus 999, 3 plus 998, etc. And how many times am I adding up 1,001? Well, if I had 1,000 terms in the original series, now I have half as many terms. So I have 500 terms. And so I end up realizing that I can calculate 1 plus 2 plus 3 up to 1,000 by 1,001 times 500. That's 500,500. And this is kind of a famous point in the history of math. I think it was Gauss whose math teacher assigned him to go and sum all the numbers to 1,000 so that he wouldn't annoy her for at least one class. And he came back later, 5 minutes later with the answer and shocked her. How did he do it? This is what he did. And we can extend this formula to the general case of U1 with a specific d and an unknown number n terms. All right, so I'm going to do the same thing. I'm going to wrap the terms. I'm going to write them vertically, and I'm going to wrap them back up to the right. So I'm going to match the first term with the last term, the second term with the second last term, and so on and so forth. And then each time I add them up, right? If I do U1 plus D plus UN minus D, the D's are going to cancel. I'm going to get U1 plus UN. And it's worth mentioning maybe why this is UN minus D instead of something plus D. Basically, because addition can be reversed by subtracting, I can go from one term to the next by adding, but I can also go backwards by subtracting. So if I do UN minus D, I'm going to get the second to last term. I subtract D again, I get the third from last term, and so on and so forth. So that's how I found this UN minus D minus 2D, etc. And if you're wondering why it stops at n over 2D, well, I'm assuming for this demonstration, and the formula still works in general, but just for the sake of the demonstration, that I have an even number of terms because it makes it a bit easier to illustrate. And that means that I want to stop at the middle, which is U1 plus half n over half of n times d, and the next one is UN minus half of n times d. But in any case, all these terms are going to line up. They're all going to add up to U1 plus UN. And I'm going to have n over 2 pairs of terms like this, which gives me the formula, the sum of the first n terms is n over 2 U1 plus UN. And that is the second formula that you have in your formula booklet. And in many ways, it's the one that is the most intuitive because it really comes from matching this first and last term and matching every pair of terms in the arithmetic sequence. Now, the formula is not super helpful a lot of the time because we usually don't know what UN is. It's more common that we know the first term and the common difference, and we know how many terms we want to sum, right? But what we do know already from previous work is that UN is U1 plus n minus 1 d, okay? So if I take this formula and I replace UN with U1 plus n minus 1 d, I get n over 2 U1 plus, and now I put in what I know, U1 plus n minus 1 d. But that's just going to simplify to the second formula, right? N over 2 times 2U1 plus n minus 1 d. All right, so it just comes back to the same thing. And the second formula is really just a combination of this formula with the one that we have for the general term. Okay, let's take a look quickly at this example. I have the sequence 1, 4, 7, dot, dot, dot. So it's arithmetic with common difference 3. And I'm trying to find the sum of the first 10 terms. Okay, so the first term is 1. The common difference is 3, and n is 10. So I write, using this formula, n over 2 is 10 divided by 2. Then I write twice u1, so 2 times 1 is just 2. And I'm going to add to that n minus 1, so n is 10, that's 9, times the common difference d is 3. So 2 plus 9 times 3, that's 2 plus 27 is 29, and I multiply that by 5, and I find 145. Okay, I'll give you a chance to work on an example of your own. Let's say I will give you a minute. All right, let's go over this. So I have a first term, u1 is equal to minus 4, and the 12th term, u12, is equal to 18. And I want to find the sum of the first 12 terms. So remember, I have the formula Sn is equal to n over 2, u1 plus un. This is in your formula booklet. And in this case, I'm looking for S12 is equal to 12 over 2 times u1 is minus 4 plus the 12th term is 18. So that's going to be 6 times 14, and that will give me 84. So note that we used the formula here that involves the first and the last term, and not the first term, the common difference d, and the number of terms, because I knew the 12th term already. So it makes my life easier. Now is a chance to use the other formula. So I'm going to give you another 30 seconds for this. Okay, time is up. So I have a first term, u1 is equal to 5, and a common difference d is equal to minus 3. And I want to find the sum of the first n, where n is equal to 11 terms, so the first 11 terms. So I'm going to use the formula Sn is equal to n over 2, 2u1 plus n minus 1 d. This is in your formula booklet. I'm going to plug in what I know. N is 11, so I have 11 over 2 times 2u1 is 2 times 5, plus that n minus 1 is 10, 10 times minus 3. All right, so this is 11 over 2. 2 times 5 is 10. 10 times minus 3 is negative 30. So 10 minus 30 is negative 20. So this is 11 times negative 10, or minus 110. Nice. Okay. I want to cover an exam problem before we move on to infinite geometric series. So I have an arithmetic sequence with a ninth term 20, and the sum of the first 12 terms is 180. And we have to find the value of d, the common difference, and the first term. So let's get started on this. I'm going to need to remember that u9 is u1 plus 8d, and that's equal to 20. That's going to be important. And I also need to remember that S12 is 12. I'm using the formula n over 2 times 2u1 plus n minus 1d. So 12 over 2 times 2u1 plus 11d, and that's equal to 180. And if I expand this, I'm going to get 6 for 12 over 2. 6 times 2, 12u1. And then 6 times 11 is plus 66. That's 60 plus 66d is equal to 180. All right, so now I know I have two equations. I have this, and I have u1 plus 8d is equal to 20. These are simultaneous equations, which means I can solve the system by either eliminating a variable or making a substitution. I'm going to try and eliminate u1, and I'm going to do that. If I call this equation 1 and this equation 2, I'm going to do equation 1 minus 12 times equation 2. Okay? Why do I do that? Because then I'm going to get u1 minus 12u1 on one side, and the u1s are going to cancel. So let's write that out. On the left-hand side, 12u1 plus 66d minus 12 times u1 plus 8d. On the right-hand side, 180 minus 12 times 20. So on the right-hand side, the U1s are going to cancel. That was the entire purpose. And I'm going to get 66D minus, and then 12 times 8, 10 times 8 is 80, 2 times 8 is 16, so that's minus 96D. And then I have 180 minus 12 times 20, that's 240, so this makes negative 60. Okay, so we're getting close now. If I do 66D minus 96D, I get negative 30. That's a really poor zero. Negative 30D is equal to minus 60, which means D is equal to 2. All right, so that's one part of the answer. And now I just need to find the first term. So I can go back to this formula where I had U1 plus 8D is equal to 20 and say U1 plus 8 times 2 is 16 is equal to 20. And that means that U1 is equal to 4. So these are our answers. 2 and 4. Let's check the multiple choice. The other way around. D is equal to 2, U1 is equal to 4. Nice, brilliant. So next, we're going to talk about infinite geometric series. So we mentioned earlier that the series can continue forever, which is a bit of an odd thing to think about when you're adding things up. But in the special case where the common ratio has a magnitude or an absolute value of less than 1, then each term is going to be smaller in size or magnitude than the previous one. So that actually means that if I add up, infinitely many of those terms, it's going to be finite. And that's maybe a tricky thing to think about, and I want to maybe help you with this visual. Each segment here on this line is slightly shorter than the one before. I think it's 0.8. It's like 80% the length of the one before, and they're going to get shorter and shorter every time. And you notice that these all converge to a point, right? Eventually, it does stop going anywhere. And you can think about that. A common example is to imagine the sum 2 plus 1 plus 1 over 2 plus 1 over 4, etc., right? So if I did the series 1 by 1, I would have 2, then 2 plus 1 is 3, then 2 plus 1 plus 1/2 is 3.5, and then I would do 3.75, and essentially it would keep getting closer and closer and closer to 4 if you were doing a finite number of terms. And when we do S infinity, we're essentially extending and we're saying, what does this series tend towards as n goes towards infinity? What is the limit of the behavior, okay? And the formula that we have for that is S infinity, the sum of infinitely many terms, is the first term U1 divided by 1 minus R. And I'm not going to prove this formula here because it's a little bit complicated, but if you guys want, I can post a separate video about that. So let's look at a quick example. Find the sum of all the terms in the infinite geometric sequence with U1 is equal to 4 and R is equal to 1 over 2. So I simply plug into the formula, which is in the booklet. I have 4 divided by 1 minus 1 over 2. That's 4 over 1/2. And that just makes 8. Okay? Very, very important. We have to remember this only works if the absolute value of R is less than 1, which means that R is between -1 and 1. If R is bigger, let's say R is equal to 2, and my terms are going to get bigger every time. I'm going to do 1 plus 2 plus 4 plus 8, for example, and that's not going to work. That cannot possibly converge to a finite value because I'm adding something bigger every time. So the sum is never going to stop. So I'm going to give you a minute to solve this. So I have the sum to infinity using my formula is S infinity is equal to 7 over 1 minus R, so 1 minus 2 over 3. That's going to become 7 over 1 plus 2 over 3, and I'm going to write 1 as 3 over 3, plus 2 over 3 is 7 over 5/3, which becomes, remember, if I have a fraction in the denominator, it means I cross multiply, or I multiply by the reciprocal of that fraction. So I have, that's equal to 7 times 3 over 5 is 21 over 5 is my answer. Option 3. Good. All right, so we talked about this a second ago, but when does a geometric series converge, right? So we said that it converges if and only if the common ratio has a magnitude or an absolute value less than 1, which is the same thing as r being between -1 and 1. And notice this is not an inclusive inequality. If r is equal to 1, then the series is also not going to converge because I'll just be adding the same thing every time. And we know that that doesn't actually stop at any value. So it's not too difficult to wrap your head around why that is the case. It's somewhat tricky to apply it in problems, right? If you're told that a series is the infinite series has a finite value that you can actually add it up, then it imposes a certain condition on what you might be given in a problem that can be sometimes difficult to solve for. So let's look at an example. If I have a first term of 8 and a fourth term of 2k plus 1, and I'm asked for what values of k does the series converge, right? So here I've given you the fourth term and the first term, which means you can isolate r cubed by doing the fourth term divided by the first term, because all the fourth term is just 8 times r times r times r, so 8 times r cubed, and that's supposed to be equal to 2k plus 1. And that means that the common ratio cubed is just 2k plus 1 over 8. All right. Now, if r is between -1 and 1, then r cubed also has to be between -1 and 1, which means that this fraction, 2k plus 1 over 8, has to be between -1 and 1. If I multiply both sides of the inequality by 8, I get -8 smaller than 2k plus 1 smaller than 8. And you solve that by subtracting 1 from both sides and dividing by 2. And you find that k has to be between -9/2 and 7/2. All right. Let me give you a chance to work on a similar problem on your own here. So I have a geometric sequence with consecutive terms 3 and 2k minus 1. And you need to find k such that S infinity exists. I'm going to give you 30 seconds. Okay, so again, I have consecutive terms. That means that the ratio is the common ratio r. And that means that r has to be between -1 and 1 since the infinite sum exists. So -1 is less than 2k minus 1 over 3 is less than 1. Multiply both sides by 3. -3 less than 2k minus 1 less than 3. Add 1 to both sides and I get -2 less than 2k less than 4. So -1 is less than k is less than 2 is the answer. So I have a geometric sequence with u3, and that u3 is the first term times r squared, and then u6, this is equal to 3, and u6 is the first term u1 times r to the 5. I did 6 minus 1 to get 5, and that's equal to 8 over 9. Okay, so if I do u6 divided by u3, it's going to simplify to, well, u1 r to the 5 over u1 r squared. That's equal to r cubed. And it should also be equal to 8 over 9 over 3, or in other words, 8 over 27. Now, taking the cube root of both sides, 8 is 2 cubed and 27 is 3 cubed. So r is 2 over 3. Is that good so far? Perfect. So r is 2 over 3, and now I need to find the first term so that I can use the formula for S infinity, right? So u3 is u1 times r squared, which means that u1 is equal to u3 over r squared. So that means that u1 is equal to 3, the second term, divided by, and 2 over 3 squared is 4 over 9. And that's 27 over 4 for the first term. And finally, S infinity is just going to be u1, so 27 over 4, divided by, and I do 1 minus r, so 1 minus 2 over 3. That's 27 over 4 over 4 over 1/3, which becomes 81 over 4. I move the 3 to the numerator because it's in a fraction in the denominator, and I move the 4 from the numerator in the fraction to the denominator. 81 over 4 is my final answer. See multiple choice, 81 over 4. Perfect. Cool. So we've talked about infinite geometric series, and it's a little odd that we talk about them before finite geometric series, but I actually think that finite geometric series are harder to work with than the infinite series. The formula is just not as nice. And we could derive this formula from the infinite series, but again, I don't want to spend too much time there because we have a lot of problems still to cover. But basically, the sum of a finite number of terms in a geometric series is the first term times r to the n minus 1 over r minus 1. And this is in your formula booklet in two forms, the one I just wrote, but also one where instead of writing r to the n minus 1 and r minus 1, I write 1 minus r to the n divided by 1 minus r. And it's the same thing because I've essentially just multiplied both the numerator and the denominator by minus 1. So it makes no difference. Let's take a look at an example, though. If I have a geometric sequence with a first term 27 and common ratio 1/3, then find the sum of the first four terms. Okay, so I don't know why I wrote S8 there. That's supposed to be S4. So S4 is equal to 27, the first term, times, I do 1 minus my common ratio to the power of 4, so 1 over 3 to the 4. And then in the denominator, I have 1 minus r, so just 1 minus 2 over 3. And that becomes 27 times 1 minus 81, all divided by 2/3. Now, if I expand the brackets in the numerator, I get 27 times 1 is 27, and 27 over 81 is just 1 over 3, because 81 is 3 to the 4, and 27 is 3 to the 3. So I get 27 minus 1/3 over 2/3. And to simplify this, I multiplied the top and the bottom by 3. So 3 times 27 minus 3 times 1/3 all over 2. 3 times 27, like I just said, that's 81. And I'm going to subtract 1 for 3 times 1/3. That gives me 80 in the numerator and 2 in the denominator. And that means that the sum is 40. Okay, this is a calculator question. I want you to solve this. I'm going to give you probably, let's say 2 minutes to do this. So I'm looking for the sum of the first 11 terms, which is S11. And I use the formula, which tells me that I do the first term times r to the power of 11 minus 1 over r minus 1. And I have a common ratio of negative 1.5. So this is going to be u1 times negative 1.5 to the power of 11 minus 1. And that is divided by 1 minus 1.5. Minus 1.5. That's an important difference. Okay, so I can't do minus 1.5 to the power 11 by hand, so I'm going to use my calculator. I'm just going to replace this u1 with 2.2. And then we're going to do this on the calculator. So I'm going to switch the share over to the calculator screen. So I'm going to add a fraction. So I'm going to go to math, frac. It's just a little bit easier than writing things out with brackets and division. And I have to write, you can unfortunately see the solution on the left, but whatever. 2.2 times, and in brackets, I had another bracket, negative 1.5 to the power of 11 minus 1. And in the denominator, I had 1 minus 1.5. I just want to make sure that this was, I used the right minus sign here. I used this. Yeah, perfect. And that should give me negative 76.99. So if I round that, I should be getting a negative number. Why did I get positive? That was my mistake. So when you do this fraction, you have to make sure if I do r to the n minus 1 in the numerator, I have to do r minus 1 in the denominator. So I have to do minus 1.5 minus 1. and I get 76.99. So the answer is 77.00. All right, let's switch back over to the regular screen. Nice. Negative 77.0 was the answer. So let's talk about sigma notation. This is mostly for higher level students. You are technically supposed to know this for SL as well, but it doesn't really show up on your exam as much. For the HL students, this is both important for questions and sequences in series, but also for questions in proof by induction, right? Because there's going to be a lot of questions about induction where you have to prove something about a sum. And it's very, very important that you be good at working with sums. So what does this notation mean? It's a shorthand way of writing something plus something plus something, a long sum of things. So let's say I have the sum 2 plus 5 plus 8 all the way up to 38. The way I would do that is I have essentially this, let me zoom in a sec so you can see a bit better. I have a sum, and I put underneath the sum my index and where I'm starting with the index. So in this case, the index was k, but it doesn't always have to be k. It could be I or R. It depends on the problem. And on top of the sum, I put where I'm going to stop my summation, okay? And then after the sum, I put the thing that I'm going to be adding up, and usually it depends on k. So let's look at an example. If I have the sum 2 plus 5 plus 8 all the way up to 38, then I recognize that I have an arithmetic sequence with first term of 2 and a common difference of 3, which means I can write un as using the formula 2 plus 3 times n minus 1, which is 3n minus 1. So I'm adding up in my summation, I'm adding up 3n minus 1, and I know that I'm starting with the first term, n is equal to 1. I just don't really know yet where I'm starting, because I don't know which term in the sequence 38 represents. So to find the n value, I'm looking for un is equal to 38. So 3n minus 1 is equal to 38, means that n is equal to 13. So this sum can be written in the form sum or sigma from n is equal to 1 up to 13 of 3n minus 1. And just to help you see the connection, let's actually write out the first few terms. If I plug in n is equal to 1, I get 3 times 1 minus 1 is 2. If I plug in n is equal to 2, 3 times 2, 6 minus 1 is 5. N is equal to 3 is going to give me plus 8 plus ... And if I plug in n is equal to 13, I'm going to get 3 times 13 is 39 minus 1. That's 38. So I'm just going to loop back and answer the question that we had, which was, how would you find A and D when using sigma notation? So let's say that I was working on this question. Let me actually make a small change. Let's say I have the sum from n is equal to, I'm going to make this extra tricky, from n is equal to 1 up to 11. And I have inside the brackets, let's say I have 3 minus 4n. And the question is, how do I find the u1 and d for this question? How do I find the first term and the common difference d? So the thing to focus on here is that inside of the sum, the thing that's changing each time I sum is 4n. The n is increasing by 1, which means I'm subtracting 4 every time. That means that when I do n is equal to 1, I have 3 minus 4 is negative 1, and then each time I'm going to subtract 4 again. So that means my common difference is the thing that's multiplying n. So d is negative 4. Now, as for the first term, you can think about the first term simply by plugging in n. So if I have n is equal to 1 as the first term, then u1 is just 3 minus 4 times 1 is negative 1. And if you're not 100% sure how the first term connects to the sum, just imagine that the sum of the first one terms is just u1 plus nothing else, if I'm adding up only the first term. So if I stop the sum at n is equal to 1, and I just add up that one term, I should find u1. So you plug in u1, and you will find the first term. We are going to go over an example later of how you do this in a geometric sequence, how you find the first term and the common ratio, because I think that's a little bit trickier, but it's a good question. All right, so I want you to evaluate this sum by hand. I'm going to give you 30 seconds. It looks tricky, but it's actually not that hard. Let's talk about, we have the sum from k is equal to 2 up to 5 of k minus 3. I'm going to do this one more or less by hand. So remember, I'm starting with k is equal to 2. That's where I'm starting. So I plug in that first value. K is equal to 2. I have 2 minus 3. So this is k is equal to 2. Plus, then k is equal to 3 gives me 3 minus 3 plus 4 minus 3 plus 5 minus 3. And that's where I stop because I only have from k is equal to 2 up to k is equal to 5. So this is minus 1, 0, 1, and 2. So I'm doing minus 1 plus 0 plus 1 plus 2. That's going to give me 2. All right, properties of sigma. All right, this looks like a bit of a mess, and it is. And you're not going to get really a question that directly uses these. I mostly am adding this for the higher level students when it comes to proof by induction. The hardest part of induction when you have a summation is working with sums and splitting the sums and understanding how the indices work. So I really want you guys to be comfortable with this notation and all of its properties because it's going to make the proof questions easier when we get to them next week. So one rule that I have is if I have a sum of a sum, if I have a sum of some, something plus another thing, AK plus BK, I can split the sum up. And that's just the same thing as recognizing that if I do 3 plus 2 plus 5 plus 6, for example, I can just rearrange the sum to be 3 plus 5 plus 2 plus 6. Sums are reorderable. I can rearrange the terms in any way that I want. It's not true for sum operations. All right, if I have a sum of a multiple, right? So if I have the sum of some constant c times ak, then the c is not changing as I sum things up, so I can factor that out. So let's do an example. If I was summing up 2 plus 4 plus 6 plus 8, that's the same thing as 2 times 1 plus 2 plus 3 plus 4. I can take the 2 out of the sum. I can divide each term by 2 and put it outside the sum because multiplication is distributive. So I can factor it out or factor it back in. So that's another rule. I also know that if I'm adding up a constant, if I do c plus c plus c plus c, I'm just going to have n c's in my sum. And that's the definition of multiplication. That's n times c. And finally, probably the hardest rule to wrap your head around is splitting the sum. So if I have a sum that goes from k is equal to 1 all the way up to n, I can consider that the sum as, let's say I do 1 plus 2 plus 3 plus 4 plus 5. That's the same thing as 1 plus 2 plus 3 as one sum plus 4 plus 5. So I can break a sum into two parts, and it's the same thing when I'm writing in sigma notation. It just looks a lot more confusing. So what have I done here? I've taken a sum that goes from 1 to n, and I've said, okay, let's sum first from 1 to m being some number that's smaller than n, and then let's continue the sum. Let's start with the next term from n plus 1 up to n. So I'll illustrate that connection with the finite case here. If this is the sum of k from k is equal to 1 up to 5, 1 plus 2 plus 3 plus 4 plus 5. This is the sum from k is equal to 1 up to 3 of k, and this is the sum from k is equal to from k is equal to 4 up to 5 of k. All right, so notice in the sum that the starting term of the one after the split is the ending term of the one before the split. Because when I put these two sums together, we have to be adding up all the possible indices. It's just that I've separated it into two pieces. So let's go over an example. And this example is relatively tricky, so we're going to take our time with it. I'm given that the sum of the first 11 terms in a series, so from k is equal to 1 up to 11 of a sub k is equal to 40. And I know that the sum from 1 to 7 of that same AK is 22. Okay, and I'm also told that the sum from 8 to 11 of B sub k is equal to 5. All right, bit of a mess, but we want to find the sum from k is equal to 8 up to 11 of 8 AK plus 2BK. So we use the first rule, which is that a sum of a sum I can split. So I split it into the sum from 8 to 11 of AK plus twice the sum from 8 to 11 of BK. And I know what the sum from 8 to 11 of BK is. That's just 5. We were given in the question. So this becomes the sum from k is equal to 8 up to 11 of ak plus 2 times 5, that's 10. Now, to find this part, this sum from k is equal to 8 up to 11, you have to remember that I'm given the sum from 1 to 11, and I'm given the sum from 1 to 7. So the sum from 1 to 11, if I try and like write a line here, let's say this is 1 and this is 11, this is 7, and that is 8, okay? So the sum from 1 to 11 is this plus this plus this plus this plus this plus this plus this, all of these together. I think that's the right number. And the sum from 1 to 7 is only these ones here. 3, 4, 5, 6, 7. And I'm looking for the sum from 8 to 11, which is the remaining terms here. 8, 9, 10, 11. I have one too many over here, but it's fine. And notice that these two complement each other, right? That's according to this rule. If I add the sum from k is equal to 1 up to 7 of ak plus the sum from k is equal to 8 up to 11 of ak, that's just the whole sum from k is equal to 1, from 1 up to 11 of ak. And we know what the whole sum is. The whole sum is 40. And we know that this is 22, which means that the remaining part that we're looking for has to be 18, 40 minus 22. Okay? Which means that I can write this term, this sum from 8 up to 11, as 40 minus 22 is 18. I add 10 and I get 22. So I know that's a little bit tricky. You're not going to have to solve a question like this one on the IB, but being able to solve this question will make you better at proof by induction when sums are involved. So if you do struggle with those, I would recommend you really try and master this type of exercise. So I'm going to give you an example now, and I'm going to give you 2 minutes to work on it. It's pretty similar to what we just did, just different numbers. So I'm going to give you 2 minutes. So I have the sum from 1 to 8 of AK is given, and the sum from 1 to 4 of AK is given. And I want to find the sum from 5 to 8 of 2AK minus BK. So the sum from 5 to 8 of 2AK minus BK is twice the sum from K is equal to 5 up to 8 of AK minus the sum from K is equal to 5 up to 8 of BK. Not K, BK. And this latter thing is just 5, so I'm looking for twice the sum from K is equal to 5 up to 8 of AK minus 5, okay? And the sum from K is equal to 5 up to 8 is the difference, right? The sum, K is equal to 5 up to 8 of AK. If I added the sum from K is equal to 1 up to 4 of AK, then this would all be equal to the sum from K is equal to 1 up to 8 of AK. And that should not be an equals, that should be a plus, because the 4 lines up with the 5 there. So I sum up to 4, and then I sum from 5 to 8. And I know that the sum up to 8 is 30, and I know that this is 12, which makes this 18. The sum from K is equal to 5 up to 8 is 18. So I'm doing 18 times 2. That's going to give me 36 for this part here. And I'm subtracting 5 is going to give me 31. That's my answer. We're now going to start talking about, for the rest of the session, we're just going to be solving practice problems. We're going to talk a little bit about financial applications after we do all this paper 1 stuff for maybe like 10 minutes. But the rest of the session is going to be solving exam-style problems. And I think we have about 10 problems to cover. So this first problem, we're going to be doing paper 1s first, so no calculator for the next 45 minutes. But I have a geometric sequence, and U2 is -9, S infinity is 12. And we're asked to show that the common ratio satisfies 4r² minus 4r minus 3. Okay, so let's start by writing out the things that I know. I'm going to make a bit of room. I know that U2, which is U1R, is equal to minus 9. I also know that S infinity, which is U1 over 1 minus R, is equal to 12. Okay? So if I solve for U1 in this formula, I get U1 is equal to 12 times 1 minus R. All right? And I can plug that into the previous formula, which is U1R is equal to minus 9, and say that 12 times 1 minus R times R is equal to negative 9. And let's expand all of this. I get 12, not 21, 12 minus 12R times R is equal to minus 9. And I expand all that, and I get, I'm going to get 12R minus 12R squared. And I'm going to bring the 9 to the other side by doing, actually, I'm going to leave it there, is equal to negative 9. And now I can divide everything by 3. I can say 4R minus 4R squared is equal to minus 3. And if I bring everything to the right-hand side by adding 4R squared and subtracting R, I find the desired answer, 4R squared minus 4R minus 3 is equal to 0. Okay, so that demonstrates part A. I'm just going to clear my screen. And I'm going to check off in the mark scheme. We did that, we did that, we did that, and we did that. Perfect. Part B. We're now trying to find the value of U1, okay? So we have an expression, quadratic expression for R. So we're going to try and solve that quadratic expression to find the common ratio, and that's going to help us find the first term, because just remember that we knew that U1R is equal to minus 9 from part A. So to solve 4R squared minus 4R minus 3, I'm going to use the quadratic formula. My negative b is 4 plus or minus the square root of b squared here is going to be 16 minus 4 times 4 times 3. All of that is being divided by 2 times 4. All right, what do I get? I get 4 plus or minus. Inside the square root, I'm going to have something is slightly wrong there. Oh, it's minus, there's a minus 3 here, so it's going to be a plus. Otherwise, that would give me a negative square root. So it's going to be 16 plus 16 times 3 is 48. So 16 plus 48, that gives me root 64 all over 2 times 4. All right. The square root of 64 is 8. So I get 4 plus or minus 8 over 8. So that's 1 over 2 plus or minus 2 is equal to either, so 2 is 4 over 2, so that gives me 5 over 2. And sorry, I don't know why I said plus or minus 2. Plus or minus 1. So that gives me 3 over 2 or minus 1 over 2. But now here's the thing. In the question, we are told that S infinity is equal to 12, which means that the sum to infinity exists. And that means that the common ratio has to be less than 1 in magnitude. So 3 over 2 does not work. We have to reject it since S infinity exists. Okay, so 3 over 2 is not valid. That means that R is just equal to minus 1 over 2. And that's going to allow us to find the first term, because I said U1 times R is equal to minus 9. So U1 times minus 1 over 2 is minus 9. And I multiply both sides now by negative 2, and I'll get U1 is equal to 18. And that is my final answer. Let's check multiple choice. 18. Beautiful. Nice work. So I have a geometric sequence with a first term of U1 and a common ratio R. And I'm given that the sum from 1 to infinity of UN is 4. All right. Now, the sum from 1 to infinity is just S infinity. There's nothing really complicated happening there. And that is U1 over 1 minus R. And that's equal to 4. all right? And then I'm told that the sum of all the terms squared from 1 to infinity is 8. So let's think about what that's going to look like. If my original geometric sequence is, I'm going to make some room and write on the right here, u1, u1r, u1r squared, etc., then if I square every term, I'm going to get u1 squared, u1 squared, r squared, u1 squared, r to the 4, dot, dot, dot. Okay, so the pattern here is I have a first term of u1 squared and a common ratio of r squared, right? I go from u1 squared to u1 squared r squared, and so on and so forth. So I have this second sum to infinity, which I can write as, again, u1 squared, first term, divided by 1 minus, in this case, my common ratio is r squared. That is equal to 8. All right, so now I have two equations, and I can start to try and solve this. It's a little bit of a mess, but if I take the first equation and I isolate u1, I get u1 is 4 minus 4r. Okay, and actually I'm going to write that. It's gonna save me a little bit of algebra if I write just 4 times 1 minus r. And if I substitute that into the second equation, I'm going to get 4 times 1 minus r. And all of that is squared because it's u1 squared here. And I'm dividing that by 1 minus r squared. And here is sort of the trick. 1 minus r squared is a difference of squares. And a difference of squares is a squared minus b squared is a squared, sorry, it's a minus b times a plus b. So this is 1 minus r times 1 plus r. I'm just going to make a note. A squared minus b squared is a plus b, a minus b. This is a classic sort of IB exam trick. You should have this really, really super familiar because there are a lot of problems that are going to expect you to kind of just like know that that's something that you can use, and it's going to simplify some of the working massively. It's not that there's no other way to do this. It's just it makes the working way, way easier. Okay, and that was all equal to 8. But before I write equal to 8, I want to realize that in the numerator, I'm going to have 4 squared is 16, and then 1 minus r squared. But I have a 1 minus r in the denominator as well. So one of them is going to cancel, and I'm going to be left with 16 times 1 minus r over 1 plus r is equal to 8. Okay, and now we're basically there because I'm just going to make a little bit of room here. If I multiply both sides by 1 plus r, I'm going to get 8 times 1 plus r is equal to 16 times 1 minus r. So 16 minus 16r is equal to 8 plus 8r. All right, what does that mean? It means that if I do 16 minus 8, I get 8 on this side, and I bring the 16r to the other side, is 24r. That means that r is equal to 1 over 3. 1 over 3, okay? And the question is asking us to show that u1 is equal to 8r is equal to 8 over 3. So we already know that 8r, based on this, is equal to 8 over 3. So that's 1/2 of what we want to show demonstrated. The only thing that's left to do is to solve for u1. We want to show that u1 is the same as 8 over 3. And to do that, I'm gonna try and make some room here. So just remember what I know. I know that r is equal to 1 over 3, which means that 8r is 8 over 3. And I already knew that the sum to infinity of the first sequence was u1 over 1 minus r is equal to 4. Now, if I plug in what I know, I have u1 over 1 minus 1/3 is 2/3. That's 4. Multiply both sides by 2/3, and I get u1 is equal to 8 over 3. All right, so that proves the second part of this. And I know now that u1 is equal to 8r is equal to 8 over 3. Okay. we're going to move on to part B. I'm just going to save the thing. Well, I guess it's a show that, so we don't need to actually write that down. We can check ourselves off with the mark scheme. That's what we did. We did that. We did that. Yep. And we did that. Nice. Okay. Now we want to find the sum of the cubes of the initial sequence. So remember, in part A, we recognized that the sum of the squares was a geometric sequence with u1 squared as the first term and r squared as the common ratio. And now we have a series that's going to look like u1 cubed r cubed, u1 cubed r to the 6, etc. Okay? So I'm gonna use a for the first term here because we're already using u1. So the first term of this sum is u1 cubed. And I'm going to use capital R for the new common ratio is r cubed. All right, and then the sum to infinity is just going to be a over 1 minus r, which is u1 cubed over 1 minus r cubed. But let's remember what we know. I know that u1 is equal to 8 over 3, and r is equal to 1 over 3. So this formula becomes 8 cubed over 3 cubed divided by 1 minus, and here I'm going to have 1 minus 1 over 3 cubed is 1 minus 1 over 27. And we're going to have to be clever in simplifying this. I'm going to multiply the top and the bottom by 27 to cancel some things out. And oops, I forgot up here, this is supposed to be a 3 cubed, sorry. Multiply both the top and bottom by 27 to cancel the over 3 cubed and the over 27 here. So I'm going to get 8 cubed over 27 minus 1 is equal to 8 cubed over 26. And 8 cubed is 8 times 8 times 8. And this is 2 times 13. So I can cancel that, and I can say 8 times 8 times 4 over 13. So 8 times 8 is 64, times 4 is 256. So 256 over 13, that is my final answer. So I'm going to clear the screen and check off multiple choice. 256 over 13, that's my answer. So I have a line that's 6 meters in length, and it's divided into an infinite number of smaller segments, okay? And the segments form a geometric sequence with lengths k, k squared, k cubed, etc. So basically, you can imagine here that we have a geometric sequence where the numbers are representing lengths, okay? And I can tell by looking at this diagram that the lengths all add up to a finite number. We're told that it's 6. That also tells me that the geometric sequence converges. So the common ratio has to be between -1 and 1. And what is the common ratio here? Well, I have first term k, second term k squared, third term k cubed, etc., which means that the common ratio is k. And the first term is also k. So I have u1 is equal to k, and r is equal to k, both of those things. So if I write the sum to infinity, that's going to be u1 is just k over 1 minus k, and I'm told that that's equal to 6. All right, so how do I solve this? I multiply both sides by 1 minus k, and I get k is equal to 6 times 1 minus k, which is 6 minus 6k. If I rearrange that, I get 7k is equal to 6, which means that k is equal to 6 over 7, which is indeed has a magnitude less than 1. So let's just check that off. We found 6 over 7. Nice. All right, and now it's getting a little bit trickier. In part B, we have an infinite sequence of squares, and the squares have side length k, k squared, k cubed, etc. So we have the same diagram as we had above with the lengths, except now we're building squares with those side lengths, okay? And we're thinking about, in part B, the combined area of all the squares. Well, what's the area of a square? It's just the side length times the side length, because the side lengths are the same. So the area of the first square is k squared. Sorry, that should be a1. a1 is k squared. a2 has a side length of k squared, and I square that, I get k4. And a3 is going to be k to the 6, and so on and so forth. So here I have another geometric sequence with my first term being a1 is k squared, and the common ratio is also k squared, okay? So S infinity is equal to k squared over 1 minus k squared. But I know that k squared is 6 over 7. So this is going to be 6 squared over 7 squared, all over 1 minus 6 squared over 7 squared. Simplify this, I'm going to multiply the top and the bottom of the fraction by 7 squared. I'm going to get 6 squared divided by 7 squared minus 6 squared. Minus 6 squared, all right? And that is going to give me 36 over 49 minus 36, which is 36 over 13, right? And let's just double check with the multiple choice. 36 over 13. Perfect. Okay, now we're getting to, the hardest part of the question. We're told that there's a line that passes through all the squares, and it divides them into two regions of equal area. And you can see that in this diagram. I have this orange region and this white region, and we're told that those have the same area. Okay, a little bit tricky, but let's think about what we know about this line. We already know from the question that we were given that the length of this is 6 meters, okay? Which means that this, the x-intercept of the line has to be 6 meters because it passes through all the squares. Okay, so that's going to be 6 meters. And then I know that the total area of all the squares is 36 over 13. And what I can notice here, I see that the area under the line, which is supposed to be half the area according to the question, is actually just a triangle. This area here is a triangle. Okay, so I know that the area, let's call it the area half, is equal to half base times height. And we know that's supposed to be equal to half the total area, and the total area is 36 over 13. So this is 18 over 13. All right, so this is just the formula for the area of a triangle. And I know what the base is. I know that the base is 6 because I know that it's given in the question. So this means that half of 6 is 3. 3h is equal to 18 over 13. All right, if I divide both sides by 3, that means that h is equal to 6 over 13. What is h? H is the y-intercept of the line. It's the height of the triangle, so this is h here. That's h. And I know, therefore, that if L has equation mx plus c, then that's the y-intercept, which means that I now have a line mx plus 6 over 13, because I know what the height of the triangle is. And all that's left to find now is the slope, okay? But now I know 2 points on the line. I know the y-intercept, 6 over 13, and I know that the x-intercept is 6, which means if you look at this line, you look at its slope. I'm gonna try and erase a little bit. This, when I kind of move down this line, I'm going down 6 over 13, and I'm going across by 6 meters, or 6. Okay, so that means that I have a rise over run. My rise is negative 6 over 13. And my run is 6, which means that the slope, m, is just negative 1 over 13. All right, so what is the final equation of the line? Negative 1 over 13x plus 6 over 13. All right, nice, well done. That's a tricky question. Let's just check with the multiple choice. Negative 1 over 13x plus 6 over 13. There we go. I have an arithmetic sequence. It has u1 is equal to 2a minus b, and u4 is equal to 2b minus a, and u7 is equal to 6b minus a. And we want to show that d is equal to negative 4a. All right, so every term here is given in terms of a and b, but we know it's arithmetic. So I know, for example, that u1, u1 plus 3d is equal to u4, and u4 plus 3d is equal to u7. Okay? So that means the difference between u7 and u4 and the difference between u4 and u1 is the same. So u4 minus u1 equals u7 minus u4 is equal to 3d. Okay? We're going to use that in a second, but for the moment, if I have this formula here, that means that u1 is equal to 2a minus b. That's given in the question. If I add 3d, I'm going to get u4, which is 2b minus a. And if I rearrange this, I get 3d is equal to 3b minus 3a, which means d is equal to b minus a. I'm going to say that u7 is equal to u1 plus 6d. I'll just note over here, this is u1 plus 3d is equal to u4. u7 is equal to u1 plus 6d. So that means that 6b minus a is equal to 2a minus b plus 6d. Right? If I simplify that, it means 6d is equal to, I'm going to get 6b plus b is 7b minus 3a, okay? Which means that, okay, so now I have two equations for d. I have d is equal to b minus a, and 6d is equal to 7b minus 3a. So I'm going to substitute from this equation into this one. So 6 times d, I replace with b minus a, is equal to 7b minus 3a. So 6b minus 6a is equal to 7b minus 3a. Simplifying that, I'm going to subtract by 7b on both sides, get negative b is equal to, and then add 6a to both sides, 3a. So negative b is equal to, negative b is equal to 3a. And I know that the common difference is b minus a. So d is equal to b minus a. And this, by the way, means that b is equal to minus 3a. So I substitute that in and I get minus 4a. That's what I was looking for. So that's a little bit tricky, all these unknowns floating around, but we got to our answer. Check this off in the mark scheme. Yeah, we did that and we did that. Perfect. Okay. Now we are told that the sum of the first 8 terms in the series is 144, and we want to find the value of u10. All right, so how can we think about this? What we know from part A is that u1 is equal to 2a minus b, and I know that b is equal to minus 3a. That's given in the question, and we found this in part A. That means that u1 can be written as 5a. We also know that d is equal to negative 4a. All right? And that's pretty helpful because now I can say that S8, not S infinity, sorry, S8 is equal to, remember the formula for an arithmetic sequence is, for the sum of an arithmetic sequence is n over 2 times 2u1 plus n minus 1d. So n over 2 here is 8 over 2. 2u1 is 2 times 5a plus, and then n is 8, so n minus 1 is 7 times negative 4a. And that is all equal to 144. All right, if I expand all this out, 8 over 2 is 4. 2 times 5 is 10a, so this gives me 40a. And then 7 times negative 4 is negative 28a. If I multiply that again, I'm going to get, actually, it's going to be easier if I, instead of doing that, I'm going to keep my numbers simple. Replace this 8 over 2 with 4. And I'm just going to divide both sides by 4. It'll keep the numbers smaller. That means that 10a minus 28a is equal to 144 over 4. So 144 over 2 is 72. Divide by 2 again is 36. And then 10a minus 28a is negative 18a is equal to 36, which means a is equal to minus 2. All right, we're almost at the answer now because that means that I know that the first term is negative 10, and I know that the common difference is 8, okay? And then u10 is equal to u1 plus 9d, which is minus 10 plus 9 times 8. Sorry, not 9 times 7, 9 times 8 is negative 10 plus 72. That's 62. Let's check our answers. Well done. Perfect. I know that some of these problems are hard, guys. So thank you for sticking with me. All right, that was all the paper 1 problems I wanted to cover. Before we do the paper 2 problems, I want to talk quickly about compound interest. It doesn't show up too much at higher level. It's more common at the standard level, but it definitely can show up on your exams. And basically, we realized that we can use geometric series to model this phenomenon of compound interest. So if you put savings, if you make a savings account or an investment account that pays interest, then that interest will compound. What does that mean? It means that if I put $100 into the bank and I get 5% per year, at the end of the year, my bank account is going to be $105. And then in the second year, when the 5% is added, the 5% is not just being added to my 100, but I now also have 5% of 105. So the money that I gain every year in interest is also going to gain interest, and that's what we mean by compounding. You kind of have this snowball where the compounding makes the value of your account bigger, and the bigger the value of your account, the bigger your interest is going to be. Okay, so I can model this by, let's say I have we use these notations, FV for future value and PV is present value. So present value times R, which is the amount that my account is going to grow by every year to the power of the number of years, would give me the value of my account in the future. But in general, when we talk about these things, we're not going to be told the ratio, the common ratio. We're going to be given a percent interest. So I might be told that I get 6% interest per year, which is the same as 6%, by the way, is equal to 0.06. And that doesn't mean that I'm multiplying my account by 0.06. It means I'm gaining 0.06 times the value of my account per year. And I keep my existing account value. So I do 1 plus 0.06 means that the multiple that I'm earning per year is 1.06. Right? In general, if I have R%, I have to do 1 plus R over 100 because I have to convert from percent to decimal to find the multiple that I'm earning per year. Now, this gets a little bit trickier if you think about the fact that a lot of savings accounts and bank accounts don't just pay interest annually. They might compound at a smaller interval than that. So it's possible, for example, that you're going to get interest not every year, but every quarter. And typically, in IB problems, you're going to be told the percentage, nominal annual interest rate. We're going to talk about what that means in a second, which is how much interest you're going to gain per year if there was no compounding within the year, okay? So if there are compounding periods within the year, if there are K compounding periods, then we have to modify our formula slightly. So let's say I was going to make 6% over a year, but the compounding is being split up over 4 periods, so quarterly. That means that I'm actually going to gain 1.5%. Instead of 6%, I divide by 4, 1.5% 4 times per year. And that makes a big difference because if I compound quarterly, then the second time that I earn 1.5%, I'm not just earning 1.5% on what I had at the beginning of the year. I'm earning 1.5% on the initial value plus the 1.5% that I already earned. So the more compounding periods you have in a year, the better it is for your savings. All right. And in general, I can find the multiple that I'm going to get per compounding period. Remember, if I said if there was one per year, it was just 1 plus r over 100. But if I have k compounding periods per year, I have to divide that percentage by k, like I did 6% divided by 4. So I multiply this by k. Okay? But then, if this is the multiple that I earn per compounding period, then I don't just put this to the power of the number of years. I have to put this to the power of the number of years times the number of compounding periods per year. So if I'm compounding 4 times per year, and let's say I'm interested in what happens after 3 years, I'm going to compound 1, 2, 3, 4 times in the first year, 5, 6, 7, 8 times in the second year, and then 9, 10, 11, 12 times total in the 3 years. So I'm going to have 12 compounding periods, which means that the multiple that I'm applying to my account gets applied 12 times. In general, it's k for the number of compounding periods per year times the number of years, right? And this is the multiple that you're going to earn over n years. So the multiple means it multiplies what I had for my starting value, and that is going to be my future value, okay? And this formula is in your formula booklet. So the good news is you don't, strictly speaking, need to fully understand the intricacies of how this, savings stuff works. I think it is helpful for a lot of problems to actually understand what's happening, but the formula is very, very clear. And generally the questions are not too hard to decipher what the value of R is, what the value of K is, what the value of N is. So it shouldn't be too hard. So let's move to the next slide. I want to talk very, very quickly, and I did a little bit on the previous slide, about the difference between the nominal interest rate and the effective interest rate, right? So let's say that I have a nominal interest rate of 6% per year. That means that if my interest was being compounded only once per year, then the growth in the value would be R% per year, okay? But like I said before, most often interest is calculated in compounding periods that are shorter than a year. So if I compound k times per year, then at the end of each period, the value grows by r over k%, all right? And that's equivalent to multiplying by 1 plus r over 100k. Now, what is the effective annual interest rate? The effective annual interest rate is the resulting growth that you would get at the end of the year if you applied compounding at every period, okay? So if I multiplied by 1 plus r over 100k by over 100k, and I did that times itself k times, that's the same as doing 1 plus r over 100k to the power of k. And that means that the effective annual interest rate is, I want to convert that into a percentage. So I multiply all that out. I subtract 1 because I remember that I'm trying to figure out the growth in my account, not how much my account has multiplied. So if my account, if I started with $100 and I end with $150, I only care about the 50% that my account has increased, right? So 50 from 100 is 50%. I don't really, it's not super relevant in the context of the interest rate, what my value actually ended at. So I figure out that I grew, my account is now 150% of what it was at the beginning, which is 1.5 as a multiple. I subtract 1, which means I have gained 0.5 times the value of my account. As a percentage, that's 50%. I multiply by 100. And that's going to give me the effective annual interest rate, all right? I know that's a bit of a word soup, and all these terms are kind of not super relevant unless you are, actually starting your savings account. But let's do an example. If I have a savings account that pays an annual interest rate of 6%, and interest is applied quarterly, so every 3 months. So I'm going to get interest in like March and then June. I don't know, every 3 months of the year, to be honest. Find the effective annual interest rate. Okay, so I have R% is equal to 6, and I have K is equal to 4, the number of compounding periods per year. I'm just going to use my formula. It's the formula on the previous slide. So PV times 1 plus R over 100K to the power of Kn. So I'm going to do 1 plus 6 over 4 times 100, so 6 over 400. I put that to the power of 4. and I get 1.06136. I did that with my calculator. If I round that, it should actually be 1.0614. So this should be 6.14. So I take that, I subtract 1, and I get 0.0614. And I multiply by 100, and I get 6.14%. I'll have to fix that value. I'm going to give you guys 1 minute to solve this problem. You can use your calculators. So yeah, go ahead. So Maria invests $1,000 in a savings account that pays a nominal annual interest rate of 7% compounded quarterly. So let's remember the formula. I have FV is equal to PV times 1 plus R over 100K to the power of Kn. And this is in your formula booklet, okay? So the present value is 1,000. I start with 1,000. And I'm going to do 1 plus 7 over 100. And I have, if I'm compounding quarterly, it means every quarter of a year. So 4 times per year. So that times 4 to the power of, and I'm doing 5 years times 4. Okay, so this I'm going to have to do with my calculator because you cannot really do this by hand. And you're essentially going to do 1,000, and then you're going to write, you can write this as a fraction on your calculator, 1 plus 7 over 400 to the power of 20. Okay, so I'm going to do that. I get 1,414.8 or $0.7, okay? And I'm going to round that to the nearest dollar, which is 1,415. All right, we're going to do one sort of like exam style problem on finance. This is sort of a classic way that sequences in series might show up on a paper too, especially for standard level students. This one is super important, and it's such easy points to get, honestly, because you have the formula, right? But Esther is going to invest $12,000 in an index fund that pays 8% interest per annum, and we're going to compound monthly. So if I'm compounding monthly, it means that I'm compounding 12 times per year. And I have R is equal to 8. Okay? So an expression for the value of Esther's investment after n years. Okay, so I have the equation. Future value is present value times 1 plus R over 100K to the power of Kn. All right, so the present value is 12,000. And I'm multiplying that by 1 plus 8 over, and then it's K times 100. So 8 over 100 times 12, all to the power of 12n. Okay, so this is a perfectly fine expression. You can simplify it a little bit. We can do 12,000 times 1 plus 0.08 over 12 to the power of 12n. And that is going to be the format that we want the answer in. So 12,000 times, no, it's not that because there's no 12n. It's not that, it's this one. Perfect. All right, let me erase that. Now, part B. Calculate the amount of interest Esther will earn over the first 4 years. Okay, so we're not trying to find how much Esther is going to have at the end of 4 years. We're trying to find how much she's going to gain over 4 years. So I'm going to take my formula. I have 12,000, and I'm going to plug in n is equal to 4, okay? How much she's going to have at the end of 4 years. So 1 plus 0.08 over 12 to the power of 12 times n is 48. This you have to do with your calculator. So 1 plus 0.08 over 12. That gives me 1.00666 recurring. I put that to the power of 48, and I get something like 1.375666. And I multiply that by 12,000, and I find that she will have 16,507. Or if I round, sorry, I should round up 508 because it's 507.99. So 508. Okay. So that means that if she started with 12,000 and she ends with 16,508, I need to subtract 12,000 from that number to find how much interest she has gained, okay? So if I do that subtraction, I'm going to get 16,000 minus 12,000 is equal to 4508. All right, and we can check our answer there. 4508. Beautiful. Let's see. Esther wants to use the money to buy a car for $27,000. Okay, so we want, the value of her account to reach 12,000. Let's remember what her account was. It was 12,000 times 1 plus 0.08 over 12 to the power of, we said 12n. And we want that to be bigger than or equal to 27,000. So this is a calculator question. You could solve this by dividing both sides by 12, taking a log, whatever. I think it's more straightforward when you get a question like this to simply use your calculator. So I'm going to show you how to do that. On my calculator, I'm going to go to the graph, and I'm going to plot the value of Esther's account. So we said it was 12,000 times, and I have 1 plus, and we said it was frac 0.08 over 12 to the power of 12x, where x is the number of years. We want that to equal 27,000. Now, in part B, we figured out that after 4 years, she had about 16,000. So I know it's definitely going to take more than 4 years. So I'm going to plot this for the first 20 years because I'm going to assume it might take a while. And I need to set my y max to include 27,000. So I'm going to set this to 30,000, and I'm going to graph this. Okay, so the blue line represents the value of her account, and the red line is the 27,000 threshold. So I go to calc, intersect, first curve there, enter, enter, enter. And I find 10.17. All right, so after 10.17 years, she would have enough money to buy a car. But we can't, give the number of years as 10.17. If we're asked for the number of years, a number, it means we have to round. But we can't round down because after 10 years, if I kind of go to 10, at 10, she will only have 26,635. So it's not enough, right? She needs to have 27,000, which means that actually the answer is going to be n is equal to 11 years, okay? 11 years is the answer. All right. By the way, on your calculator, you also have and maybe it's worth showing you quickly. I don't use it, and I would only recommend using it if you like it and you get it. But you do have an app on your calculator that can solve, it's app number 1. It can solve financial problems. So it's the TVN solver, and you can put in things that you know, and it'll find, it has the same values as we saw before. It has n for the number of years, I% is the interest rate, the nominal interest rate, PV is the present value, payment is how much you're paying, or like if you're paying into the account, which usually we're not going to do in the context of IB, at least in AA, number of payments that you make per year, and the number of compounding periods per year. You can also solve for the interest rate or PV or N or whatever using this app, but it's really not going to do anything different than what you know how to do already with your calculator. And in general, you do so much more. Basically every second problem on paper 2 requires you to graph or find intersections or something like that. I would much rather that you get really, really good at graphing functions and finding intersections and solving things like that than going and learning another app that's going to do the same thing anyways. That's my personal recommendation, but if you like the app, use the app. And we're going to now move on to some harder paper 3 problems. I don't know why I put this one again. We already did that earlier, so we're going to skip. Okay. Here is another annoying problem about sums in sigma form, okay? I don't like these either, by the way, so you're not alone in your pain here. But let's try our best. So I have the sum from n is equal to 1 up to infinity of x to the n plus 1 over 2 to the n minus 1. And someone asked me earlier, someone asked the question, how do you tell by looking at sigma what the first term and the common difference is? And in this case, we're going to see how you can tell the first term and the common ratio, which is, I think, a little bit trickier. But what I'm going to do is I'm going to take the part that's inside the sum. So I have x to the power of n plus 1 over 2n minus 1, okay? And if I factor out x squared, I'm going to get x squared times x to the n minus 1 over 2 to the n minus 1. And why do I do that? I do that so that the x and the 2 both have the same power. It's going to make it a little bit easier to understand what's happening. So I'm going to have x squared times x over 2 all to the power n minus 1, okay? And that means that since x is not being changed in the sum I can just rewrite as this x squared times the sum of x over 2 to the power of n minus 1, from n is equal to 1 up to infinity, all right? And I want to find the first term u1 and the common ratio r. So if I let n is equal to 1 in the sum, then I'm going to have 1 minus 1 is 0, and anything to the power of 0 is going to be 1. So x over 2 is just going to be 1, and all I'm left with is x squared. So u1 is equal to x squared. And then what's the common ratio? Well, the common ratio is the thing that I'm going to be multiplying by to get from one term to the next. So every time I increment n by 1, I go from x over 2 to the power of, let's say, 1, and then to the power of 2, and then to the power of 3. So each term is being multiplied by x over 2, which means that the common ratio is x over 2. Okay, so let's check that off. u1 is x squared, and r is x over 2. There we go. All right, I'm going to erase this, and then we're going to try and solve part B. So we want to find the range of values x for which the series converges. And remember that a series converges when the magnitude of the common ratio is less than 1. So r is less than 1. Or in other words, -1 less than r less than 1. And I know that r, we said, was x over 2. So I have -1 less than x over 2 less than 1, which means that I have -2 less than x less than 2. Let's check our answer here. Beautiful. And this one is wrong because there's an inclusive inequality, and it's it's an exclusive inequality that we want for the common ratio. Okay, and now we are told that this sum to infinity is equal to 50 over 3. All right, and a sum to infinity, remember we have the formula u1 over 1 minus r, and we're told that that's 50 over 3. What is u1? Well, we said u1, in part A, we said that u1 was x squared, and r is x over 2. So this is 1 minus x over 2. If I set that equal to 50 over 3, and now I multiply both sides by 1 minus x over 2, I'm going to get x squared is equal to, x squared is going to be equal to 50 over 3 times 1 minus x over 2. And this is a little bit messy. So what I'm going to do is I'm going to multiply both sides by 3 to simplify a little bit. 3x squared is equal to 50 minus, and then 50 times x over 2 is minus 25x. Now, if I rearrange this, I'm going to get a quadratic. So I have 3x squared plus 25x minus 50 is equal to 0. I'm going to use the quadratic equation. Or actually, you know what, even better, I have a calculator. It's a calculator question, and I'm going to show you how to do this on a calculator. So let me switch over to the calculator screen. You have an app on your calculator, at least on the TI-84, and I think there's something similar on any calculator you might use. But you can go to this ELY SMLT2 and to the polynomial root finder. And this can find the roots of not just quadratics, but also cubic equations and quartic equations, etc. But in this case, I'm going to put order 2 because I have a quadratic. I'm going to go next, and I'm going to enter in my quadratic. And I had 3. I believe it was then 25 minus 50. And if I solve it, I find 2 roots. I find 5 over 3 and negative 10. So let's go back to the problem and write down what we just found out. Okay, we found out that x even, not r, x is either equal to negative 10 or x is equal to minus 5, sorry, not minus, positive 5 over 3. But remember that in part B, we figured out that x was between negative 2 and 2. That was the only range of values of x that made the series actually converge. So what happened here was the quadratic that we found was a necessary condition. That quadratic had to be true for this summation to be true, but this value x is equal to negative 10 does not make this true. Okay, so it doesn't actually work in the summation. So we have to reject this, and the answer is x is equal to 5 over 3. 5 over 3. So in this problem, we have 3 different people. We have Alice, Bob, and Carol, and they're all planning for their retirement. Okay, so they're currently 25 years old, and they each aim to save $500,000 by the time they retire at age 65. Okay, so Alice decides to invest $60,000 in a savings account, offering an interest rate of 6% per annum compounded annually. And in part AI, we want to find the value of Alice's savings after 40 years. So remember, FV is equal to PV times 1 plus R over 100 K to the power of Kn. In this case, we're compounding annually, so K is just 1. The PV is the 60,000 and R is 6%. So this is equal to 60,000 times 1 plus 6 over 100 to the power of 40. Okay, so I'm going to calculate that. 60,000 times 6 over 100 is 6%, plus 1 is 1.06 to the power of 40 gives me 10.28. And then I'm going to multiply that by 60,000. And she's going to have $617,143. And as usual in IB, if we're not told how many decimal places or what precision to give the answer, we're going to give it to 3 significant figures. So 3 significant figures here means I keep the 6, the 1, and the 7, and my answer is 617,000. 617,000. There we go. Now, part AII. We're trying to find the age, Alice's age, when her investment reaches the target. So the target is 500,000, which means according to her savings plan, she's actually going to exceed her target, and we're trying to find when she's going to reach that target, right? So after how many years is her account going to have a value of 500,000? So this is going to be another calculator kind of question. I'm going to share my calculator screen, and we're gonna go over this. That is working, very good. Okay, so we said that the value of her account was going to be 60,000 times, let me put a bracket, 1 plus, do a fraction here, 6 over 100 to the power of x, the number of years. And we want to figure out when she's going to have 50,000. Right, so before I hit enter, let's just check my window. We know that when she's 40, she's going to have 600,000, so it's going to be less than 40. So between 0 and 40 for the x window. And the y window, we can do 0 to maybe let's do 600,000 because we want to see the line 500,000. So let's graph this. My window is wrong. 500,000, and I need to have an extra 0 here. So that's my bad. Graph. There we go. Now we see the intersection. The blue line is her savings. The red line is the target. Okay, so we're going to go to intersect. Enter, enter, enter. 36.38 years. Okay, now because the compounding is happening annually, Alice is going to have to wait 37 years for her savings to reach that value. And since she started when she was 25 plus 37 is going to be 62. So let's put that answer in. I need to charge my iPad because it just died, so I can't actually show you any working. 62 is the answer. In part B, Bob is investing 46,000 in a savings account, offering an interest rate of 6% per annum. So the same percentage interest rate, but he's investing less, but his is going to compound K times per year. And we want to find the minimum value of K such that Bob's savings reach the target within 40 years, okay? But basically, we're going to use the same formula. FV is equal to PV times 1 plus R over 100K to the power of NK. And in this case, we just have the same R as last time, 6, and the only thing that's changing is that K is equal to, K is an unknown here. So I have FV is equal to PV times 1 plus R over 100K to the power of N, the number of years, okay? And we want Bob's savings to reach the target within 40 years. So if we put what we know, which is 46,000 times 1 plus 6 over 100K, and let's not forget, I forgot the NK there because it's K compounding periods per year, to the power of 40K, we want that to be bigger than or equal to the target of 500,000. So this is going to be a calculator thing again. I'm going to type in the equation for his savings. So 46,000 times 1 plus, let me do a fraction again, 6 over 100x. And now I'm letting x be the variable k. On the calculator, you just have to use x when you're in function mode. And to the power of 40x, 40k again. And I'm going to change the window because I don't know if we need 40 compounding periods per year, but we can assume, I'm going to start by assuming it's somewhere between 1 and 12. So it's somewhere between annual compounding and monthly compounding. And we still need the line 500,000 because we want to see for what value of k it's going to exceed that. And I can graph this. Let's see. All right, so a little bit tricky to see here, but the blue line actually is going to be exceeding the target eventually. And I can make it a bit clearer if I make this 400,000. You can see that a little bit better. Okay, now if I do the intersection by going to calc and intersect, first curve, second curve, and guess. Okay, x is 5.09. So k is 5.09 is the minimum value of k such that Bob's savings reach the target. But k is a number of compounding periods per year. I can't compound 5.09 times per year. I have to compound either 5 or 6. But if I did 5, I would be to the left here. I would be at 5, which would only get me to 499,000. I wouldn't have enough, or Bob wouldn't have enough to retire. So we actually need to round up to 6, at which point he's going to have 501,000. So the answer here is k is equal to 6. K is equal to 6. All right, nice. Now, Carol decides not to put her money in an investment account, but instead she makes yearly deposits into an account that pays no interest. So she is making the rather foolish decision of not putting her money in a savings account. You should all put your money in savings accounts as soon as you have money. That's not investment advice. I'm not qualified to give investment advice. But Carol decides to put her money away, simply no interest. And each year she's going to deposit 5% of her salary into this account. And at age 25, her salary is $100,000 per year. And each year she gets a raise of Q%. Okay. So that means that in the first year, she's going to put away 5% of her salary. 5% of 100,000 is 5,000. The next year, she's going to get a raise of Q%. So she's going to make 100,000 per year. And she's going to put away 5% of that. So this is actually going to be a geometric series with a first term of 5,000. She puts away 5,000 in the first year. And in the second year, she's going to put away 5,000 times 1 plus Q over 100. Okay, and I'm doing Q over 100 because Q is in percent. So if she gets a 10% raise, she's making 110,000. 5% of that would be 5,500. So 1 plus q over 100 would be 1.1. 1.1 times 5,000 would be 5,500. So this formula works. So this is going to be, and I've got to put this to the power of n. So her savings per year, if we call it un, is that, and I'm going to do -1 because in the first year, it's just 5,000. So this is a geometric series. First term is 5,000. The common ratio is 1 plus q over 100. All right, so we are in part A trying to determine the age at which Carol will reach her goal if q is equal to 8. She's putting this money away every year, and we care about whether her savings are going to reach a target, and that means her savings are being added up every year. So we actually need to find Sn. This is going to be a finite geometric series. The first term is 5,000. Then I'm going to have r to the power of n minus 1 over r minus 1, where r is equal to 1 plus q over 100. Now, on the calculator, to make this easy, I'm going to start by calculating what r is if q is equal to 8, and then plug that into the formula, because otherwise I'm going to have fractions inside fractions, and it's going to be really, really ugly. So we said that the ratio was 1 plus q over 100, so 8 over 100. So the common ratio is 1.08. So let's just write that down. And now if I go to my function, I can write out what the sum for the first n is. So I'm going to have 5,000 times, and r is 1.08. Put that to the power of x instead of n. I'm going to subtract 1, like in the formula, and in the bottom, 1.08 minus 1. And I'm going to keep the window. She still wants to hit the target of 500,000. So let's see what happens here. I should make the window, let's make the window 0 to 600,000 for a second, see if we see anything. Okay, we need to make the x bigger. The x max was 12. Let's set, hopefully it's within 40 years, but let's just set it to 60 years. So that's age 25 to 85 and see what happens. Okay, perfect. We find the intersection. Blue line, red line, yes. X is equal to 28.5. Okay, so that's after 29 years. So it's 29 years later than when she was 25, okay? So she was 25 and she waited 29 years. But we have to remember that in the first year, when n is equal to 1, Carol is 25. So she starts putting away her money when she's 25. So we actually have to subtract 1 from the final answer. So we do 25, 25 plus 29 minus 1. That's going to be equal to 53. And I know that that subtraction can be a little bit weird. What I've seen in the past on IB mark schemes, when you have a question like this where it's not 100% clear whether someone is doing something at the end of the year or the beginning of the year, if you could reasonably interpret it both ways, then the mark scheme is actually going to accept both answers. So 53 and 54 would both be accepted. That's typically what happens, okay? So you don't need to worry too much about these questions where you have this weird edge case. Just focus on understanding the math about what we did and trust that most of the time, I haven't seen a case where this wasn't true. The IB is actually going to be fair to the answers. So 53 is going to be my answer. Let me just clear the screen here. 53. And now the last part of this question is asking us to find the minimum value of Q such that Carol reaches her savings target by the time she retires, okay? So she's going to retire after 40 years, and we want to find the minimum value of Q that makes that possible. So if I go back to my formula, earlier we said we were going to start by calculating R instead of working with Q, and then find what the minimum age if Q is equal to 8. Here I'm going to do something similar. I'm going to delete some of this. Instead of doing something to the power of x, I'm going to say x is the common ratio, and we're going to put it to the power of 40. After 40 years, that's when she retires. And we're going to delete, and we're going to say the common ratio is also x down here. And we're going to do x minus 1. Give me a sec, x minus 1. So what I'm doing here, I'm not going to find the intersection for q, because if I did that, I would have to plug in r is equal to 1 plus q over 100, and it's going to make the calculator a bit of a mess. Instead, I'm going to start by finding r, and remember that r, or in this case, x, is 1 plus q over 100. And then once I find that, I'm going to work backwards and find q. So let's graph this. Notice that my window here was 0 to 60. She's not making a 60% raise per year. Let's say she makes at most 15%. It seems like a reasonable number. And even still, she doesn't need to make nearly that much. So let's go, did I type that in right? Yes. Second calc, I'm going to find the intersection. Let's come back down here. Get a bit closer to the intersection. That's 1, that's 2, and guess. Okay, so it seems like if she makes even a 1% raise per year, she's actually going to reach her savings target, which is a little bit surprising. I wonder if I've made a mistake here. Oh, no, sorry. Yeah. I haven't made a mistake. It's because this is the value of x, the value of r, and not the value of q. So why can't you see my screen? Oh, okay, zoom. For some reason, I'm unable to draw now. Okay, x is 1.042. That's the value of x. And we said that x is equal to 1 plus q over 100. So if I subtract 1 from both sides, I get x minus 1 is 0.042. That's q over 100. And if I multiply that by 100, then I'm going to get 4.2%. And it says in the question, q is set to 1 decimal place. So 4.2 is the answer. 4.2. Oh no, that was dumb. You have to round up. Of course, you have to round up because we're asked for the minimum value. So 4.3 is the answer. Mistakes happen to all of us, I guess. I'm going to take a second here to try and fix my iPad to let it so I can write on the screen again, and then we're going to continue with the next question. That was all the problems that I had for today, but thank you for coming, and see you soon.